Hello, welcome to 13 Universal Learning Beyond Barriers. This is Shedro, and we're going to be looking at A-level CIA Biology Enzyme Series 4. So we have done Series 1, 2, 3. This is Series 4. So come with me. Let's explore enzyme questions. Some inhibitors of, that's number one, some inhibitors of enzyme reactions bind to the enzyme substrate complex, right? You see, and of course, it says which statements about this type of inhibition are correct. So this inhibitor binds to the enzyme substrate complex. That means it has a binding site other than the active site. So the active site changes shape from this statement. All right, the um, the enzyme and the substrate they have already formed a bond, okay, temporal bond, so it might not change shape. Okay, the inhibitor is non-competitive. Yes, non-competitive inhibitor because it does not bind to the active site. Non-competitive inhibitors do not bind to the active site; they bind to allosteric site. Okay, that is a site other than the active site. All right, so the initial rate of reaction is reduced. Yes, non-competitive inhibitors reduces, all right, initial rate of reaction. Let me show you something here. I've shown it before that if this is an enzyme, there's another site here, that is different from the active site, which is this. All right, so this is an enzyme. Look at this, guys. See, uh, this enzyme, this inhibitor binds to the allosteric site. It doesn't bind to active site, right? Because if it binds to active site, that means it wouldn't have attached to the enzyme when enzyme substrate complex is formed. Now look at it. If enzyme substrate complex is formed, that means the substrate. Now this is substrate. Let's assume this is substrate, okay? When the substrate binds to it, we're going to have something like this, okay? Yeah. See? So this is inhibitor. So the inhibitor, when it binds to it, we're going to have, it can still bind to, this is enzyme substrate complex. Okay, this is it is the enzyme substrate complex. See it, enzyme, this is substrate that's attached, this is enzyme. Okay, just look at it, you'll see. All right, you see that this is enzyme substrate complex, this is allosteric site where this binds to. Okay, the inhibitor binds to the allosteric site. Did you get to so you see that this inhibitor is a non-competitive inhibitor. It's not competitive. Competitive will bind to the active site. You get, and of course, normally non-competitive inhibitors, they reduce rate of reaction. Okay, they reduce rate of reaction. If you remember this graph, okay, so these are the points about non-competitive inhibitors. This is substrate concentration. This is rate of reaction. Okay, so without the inhibitor, it goes like this, levels. Now with non-competitive, it will lower the rate of reaction. So this is the rate without, see, the rate, sorry, this is the rate, this is V, all right, is the rate without inhibitor. Now this is the second V, call it V, and that's okay, rate of reaction with non-competitive inhibitor. See that it lowers it. Okay, so we have something like this. You see, number 2 is correct, number 3 is correct, number 1 is not correct because it cannot change it again. When it binds to this substrate enzyme substrate complex, it cannot alter the shape again. It can only alter the shape if the substrate has not attached to the enzymes. Okay, so look at it. The maximum rate of reaction stays, it doesn't stay the same, it decreases from here to here, it decreases. So 4 is wrong. I think 1 is also wrong. All right, so what is the answer? The answer is what? The answer is 2 and 3. The inhibitor is non-competitive. It doesn't bind to the active site, binds to allosteric site. It reduces the rate of reaction from this to that. Okay, so let's go to the next question. The enzyme DNA polymerase is used. DNA polymerase is used in DNA replication. You can see that. Yeah, they said this enzyme was extracted from bacterial lining in natural hot water springs, where the water temperature is between 85 degrees Celsius and 95. Can you see? That's extremely high temperature. Okay, it's extremely high temperature. If you look at it, which one shows this? Now, if you look at A, you see, now normally temperature has positive correlation with rate of reaction. Okay, at the beginning of the reaction. Okay, but when it reaches after optimum temperature, the enzymes active site denatures. Normally, this is the normal graph. So that is temperature, guys. This is rate of reaction. You can see that it should go like this, up and down. Now, if we divide this graph into two, guys, you see that the first part is positive. If this is part A, there's a positive correlation between temperature and rate of reaction. If this is part B, there's a negative correlation. Okay, so normally this part, look at this part here, this is the optimal temperature. Optimal temperature gives us the highest rate of reaction. So once temperature increases above it, these are higher temperatures, the rate of reaction will start dropping. Okay, now you see this is look at a temperature is increasing, rate of reaction starts increasing. Okay, now it is trying to here is trying to plateau. All right, but is this the optimum temperature? Because it when it reaches optimum temperature, it can then come down after the optimum temperature. So okay, now what do you think about A? Is it correct? Does it follow the trend? Okay, look at B. B says that the optimum temperature of this enzyme is below 660. Okay, why they told us that the temperature is 85 degrees Celsius to 95. Any bacteria that can survive here, the optimum temperature of the enzymes must fall within this range. Okay, so the same thing, this is wrong because the optimum temperature is below. Now C seems to be correct because at 60 the rate of reaction is still increasing. It hasn't reached, can you see it? See it now, it has not reached the optimum. Okay, so it keeps increasing. All right, what do you think is the answer? Okay, and that's what it says here. Which graph would represent the relationship between the temperature and the rate of DNA replication when catalyzed by the enzyme from these bacteria? Which one represents it? Which one? What do you think? Of course, it's C. All right, temperature increases with rate of reaction and until it reaches optimum. After optimum, beyond optimum temperature, the rate of reaction will decrease because high temperatures break hydrogen bonds, and hydrogen bonds help to hold the active site. And then once it's broken, active site becomes distorted and less complementary or non-complementary again, and can no longer bind to the substrate. No ES complex form. Okay, so C is the answer. Let's go to the next question. The graph shows the energy level involved in an enzyme catalyzed reaction. Energy level. Substrate molecule X and Y combine to give products. So pause the video and try it. Okay. So then answer the question says which arrow shows the reduction in activation energy due to the enzyme. The question is, what is activation energy? Tell me. Yes, what is activation energy? Yes, I'm listening. Oh, yeah, you're correct. It is the minimum amount of energy required for reaction to occur. Now, enzymes lower activation energy. Okay, so from here we have two reactions here. The first one is this. Okay, the activation energy of the first one is C. Okay, we have the second reaction which occurs at a lower energy. The activation energy is A. Okay, so the difference between A and C, that's what they're asking us, is B. Do you get it? The difference between A and C, enzyme lowers the activation energy from here to here. All right, so the difference is B. All right, please like our videos. We want to hear your comments, share the videos, and subscribe. All right, which statement about enzyme inhibitors are correct? Number one, inhibitors may be similar shape to the substrate. Is this correct? Competitive inhibitors bind to the active site. Non-competitive inhibitors alter the shape of the enzyme. Non-competitive inhibitors bind to the substrate. Now let's look at it. Competitive inhibitors, look at it. I think we've done it before, but let's see it. We'll not get tired of explaining. Okay, if you have an enzyme like this, okay, and the active site is somehow like this, okay, and the substrate is like this, okay. Can you see the substrate? And the inhibitor is somehow like this. So competing inhibitors, like we've always said, okay, this is I inhibitor, this is S substrate, this is enzyme. All right, so competing inhibitors, very importantly, they have similar shape to substrate, okay. So the first one says competing inhibitors may be similar shape to substrate. That's correct, similar shape. And because of that, competing inhibitors bind to the active site, so they can bind to the active site, okay. So 2 is correct. Now 3 says non-competing inhibitors alter the shape of the enzyme. Yeah, some of them do alter, all right, when they bind to allosteric site. So let's look at that. If you look at non-competing inhibitor, if this is enzyme, this is allosteric site, okay. Now this is yeah, this is active site, okay. So when non-competing inhibitor binds to allosteric site, okay, when it binds, when it binds here, okay, when it binds, it's going to alter the shape, okay. The shape of this enzyme will look like this, okay. It's altered, sometimes it alters like this, so that substrate is not able to bind to that, okay. All right, so yes, so there's a non-competing inhibitors bind to the substrate. It doesn't bind to the substrate, okay. It does not bind to the substrate. It binds to allosteric site on the enzyme. So which option is correct, guys? Choose one. What do you think? So 1, 2, 3 are correct about inhibitors. Competing inhibitors may be similar shape. Yes, we said that. And the competing inhibitors bind to the active site. Very important. And of course, so let's go to the next question. Okay, it says a fixed volume of the enzyme catalyst was added to a fixed volume of hydrogen peroxide. Now, fixed volume, fixed substrate. The diagram shows how the amount of product changes over the course of the reaction. Let's see. Okay, yeah, so it's which explains the shape of this graph. The active sites become saturated? No, because the fixed amount, right? So as remember that as reaction continues, substrate is being used up, okay. So active sites will become freer. So A cannot be the answer. All right, B says the enzyme was denatured. Not really, nothing shows that it's denatured, okay. You will check. C says the hydrogen peroxide inhibited the reaction. The hydrogen peroxide is the it is the substrate. Substrate is not an inhibitor, okay. Catalyst breaks down hydrogen peroxide, okay, to water and oxygen. So C doesn't look like the answer. The substrate molecules were used up exactly as the reaction continues. You see, product is in concentration is increasing, substrate is decreasing. So when the substrate molecules are used up, it levels, okay. So what do you think is the answer? Of course, is D. All right, C says which statements describe some enzyme actions? Yeah, number 1, enzyme hold reacting molecules in such a way that their reactive groups are brought close together. Yes, it does that. And during condensation, it holds two substrate molecules to form a product. Yes, that's correct. 2 says in an enzyme catalyzed reactions, more molecules have sufficient energy to react than in the absence of the enzyme. What do you think? More molecules have enough energy to react, okay. Is that correct? So see, if the activation energy without enzyme, activation energy A, let me call it A, is without enzyme is about 80 degrees. Maybe you need to supply this, okay, temperature. Let's assume it's going to give us about 300 or 30 joule, maybe 300 joule, okay. You supply this. By the time you introduce enzyme lowers it, okay. So it's going to lower the temperature maybe from 80, of course, to like 30. That's okay, 30 degrees Celsius. Yeah. So of course the energy amount here would have dropped maybe to probably to like maybe 100. Okay. So when enzyme 100 joules, when enzyme is working, all right, An enzyme's catalyzed reaction, more molecules have sufficient energy to react. So most molecules may not have up to 300 joules without enzyme, but when you use an enzyme, more of them will have 100, okay, joules to react, because you have reduced the amount of energy needed for the reaction to occur. So most molecules will have that less amount of energy compared to the high amount. So 2 is correct. 3 says the reactions catalyzed by enzymes take place at lower temperature. The same thing that they would have, okay, because temperature, if you want to supply heat, okay, energy is supplied to reaction by heating. So if you are heating, if you need high energy, you heat at high temperature, okay. But if you need low amount of energy, you will heat at low temperature. So when enzyme comes, of course you need less heat, all right, and therefore less energy is needed, therefore less temperature, okay. So the reaction will go at a lower temperature because enzyme has lowered the amount of energy needed, so less temperature or less heat, okay, lower temperature. So 3 is correct. So what do you think is the answer? Of course, the answer is A, all of them. They're all correct. Please don't forget it. These are important facts about enzymes. Is that okay? All right, let's go to number 7. Number 7 says, the diagram shows the mass of product formed over time in 3 reactions. Using the same substrate and enzyme, the volumes of substrate, enzyme, and temperature were kept constant in the reaction. Okay, look at that. So everything was kept constant. There's a which statement explains the difference in the reactions. Okay, that's A, B, C, D. Look at it. So they said product formed over time in these 3 reactions using the same substrate and enzyme. The volumes of substrate, enzymes, and temperature were kept constant in each reaction. Which statement explains the difference in these reactions? A says the pH in the reaction 2 and 3 has denatured the enzyme. No, if it's denatured it, the enzyme reaction wouldn't have continued. Look at it. At this point, the rate of reaction is still increasing. Still increasing. All right, still increasing gradually. All right. Now there's a non-competing inhibitor present in the reaction. If there's a non-competing inhibitor, it will not reach the maximum rate. Can you see that all the 3 graphs, they reach the maximum rate? So if there's a non-competing inhibitor, it will not reach, it will lower, it will reduce the rate of reaction. Okay, so that is why B is wrong. C said there is the highest concentration of enzyme in reaction 1. In reaction 1, well, enzymes active sites, all right, that are available, they don't really determine the rate of reaction here, because enzyme concentration remains the same, but substrate will be decreasing. So it's the amount of substrate that determines, all right, the mass of product formed. All right, so this is likely, all right, this one has the highest concentration of substrate. Okay, so the answer should be D. There is the highest concentration of substrate. The more the substrate, the more product formed. The less the substrate, okay, because they all enzymes active site, they remain the same as the reaction go on. As the reaction go on, enzyme concentration does not decrease, but substrate decreases and product increases. So the more substrate used, the more substrate available, the more substrate will be used, and more product will be made, and that is what 1 shows. Okay, so now let's go on. The tyrosinase is an enzyme. So please, the answer to question 7, I just jumped now, is D, the substrate concentration. All right, the substrate concentration is why it has high amount of product form. It's not C. Okay, so it's a tyrosinase enzyme is an enzyme that catalyzes the conversion of the amino acid tyrosine into the black pigment melanin. It is responsible for the black fur color of some rabbits. All right, look at it. Then I say a group of rabbits kept at 30 degrees Celsius resulted in 90 degrees Celsius. Sorry, 19%, 90%. Okay, of the rabbits with light fur color at 30. So at 30 degrees Celsius, 90% were light fur color. A second group of rabbits kept at 10 resulted in 90% of rabbits with black. Okay, at this temperature we had 90 with a light 4 color are these. That means something is happening to the catalase, the tyrase enzyme. So that means it's not functioning at 30, but it's functioning at 10. Okay, yeah, because if it's functioning at 30, there will not be light color, there would have been black. All right, just you have to read the question carefully. All right, so which hypothesis is supported by this result? A says the inhibitor is present in rabbit skin. An inhibitor is present in rabbit skin cells that can bind strongly to tyrosinase when the external temperature is 30. Yeah, this makes sense. That means at 30, an inhibitor inhibits this enzyme. Therefore, black pigment is not formed, which is melanin. Therefore, 90% are light form. A makes sense. Let's check B. B says at 30 degrees external temperature, there are fewer tyrosine, that's enzymes of the complex. This is substrate, tyrosine, and tyrosinase is enzyme, complex formed, and less melanin. No, that's not true, because at 10, we had black 4, which is we had more melanin, okay, not less. So B is wrong. C says tyrosinase is an enzyme that is coded for by a gene that is switched off when the external temperature is 10 degrees. No, if the gene is switched off, that means melanin wouldn't have been formed here. Okay, and look, at 10 degrees Celsius, 90% of the rabbits with black four color. 90%. Many of them had black 4 color. Okay, that means that the gene was active here. C is wrong. D says tyrosinase is a temperature sensitive molecule that is only activated when the external temperature is 30. If it's only activated when the temperature is 30, then I wouldn't have had 90% of them forming black 4. Okay, so you see this is giving us 4. That means it can also be activated at 10 degrees Celsius. So what do you think is the answer? I think the answer is A. Is that okay? So let's look at the next question. I want you to pause. So the graph shows the concentration of one of the substances which is involved in an enzyme catalyzed reaction. Oh, look at this. There's a which substance is shown by line X. Enzyme. So which one is constant? You know it. You know the answer. The only one that is constant is enzyme. Enzyme concentration remains the same. Enzyme concentration does not decrease, does not increase. You know, it remains the same. So the answer is enzyme. Number 10 says, what describes the induced fit model of the action of an enzyme? A says the binding of the active site to the substrate causes the enzyme to change shape. The binding of active site. Active site doesn't bind to the substrate. Okay? It is the substrate that binds to the active site. Okay? So it causes the enzyme to change shape. Alright, let's see other ones. B says the substrate and active site have complementary shapes. No, they don't have. In induced fit model, they don't have complementary shape. This explains lock and key hypothesis. C says the substrate causes a change in enzyme shape so the active site can bind. Yes, this makes more sense. D says the substrate changes shape so that it can bind to the active site. What changes shape is not a substrate, it is the enzyme that changes shape, not substrate. This is wrong. Now, they said the substrate causes a change. Yeah, it's the substrate that stimulates the change. As substrate start binding to the enzyme active site, as the substrate, it stimulates the change in the shape. All right, for induced fit model. Okay, is the substrate that stimulates change in the shape of the active site. Okay, so the answer is C. All right, so this is where we stopped now. Please follow us up, watch our videos, like them, comment, share, subscribe. So we'll continue with the next topic in next video, cell membrane transport. Thank you for following us all through this time with Enzyme. Have a wonderful time. Remember, this is schedule. See you at the other side of cell membrane and transport. Bye.